Good day, my name is Gina Fatt. These are my teammates Josanne, Batson, and Winton Pierson. Today we'll be discussing our power transmission system design. Our design objectives include reducing speed from 600 to 40 RPMs while transmitting a 6.5 horsepower. For our shafts, both the input and output shafts have to be moving in the same direction. We are applying this to medium to low precision applications with moderate shock levels and high humidity levels of 90 to 95%, with temperature ranges between 73 degrees Fahrenheit plus or minus 50 degrees. Also, we expect our design to be a low-cost application. Some of our targeted applications, as you can see, are high-pressure suspension grinding mill used in the coal industry. Right here you can see in orange the right-angle transmission system. Over on this side, we also have industrial mixers used in the food industry. And in packaging, this is an industrial conveyor belt system with the right-angle transmission right here. For our literature survey, we found many different designs and applications. The first one comes from Boston Gear. They use a worm gear transmission system. It's two-stage, so it's double reduction. And some of the applications include conveyors, whether they be belt, direct drive, or inclined, packaging machinery, and also the food processing industry. The minimum cost for this was $550. Our next design comes from Emerson Gearing. They chose to use helical bevel gearings, also two-stage double reduction. In their design, they use ball and tapered roller bearings and corrosion-resistant cast iron housing. Some of their applications include mixers and agitators, turntables, and winders. And our third design comes from a company called GAM. They decided to use hypoid gearing, which gives a 96% efficiency. They also use tapered roller bearings, and their applications include pharmaceutical, medical, and mechatronic applications.
Conceptual designs. As you can see, we have a simple design here. We start off with our input shaft and input gear, which is a helical gear going clockwise. We have the reduction gear, which is also a helical gear, which is going to be going counterclockwise. Then we have our fourth gear, which is a helical gear, and we have our fifth gear, which makes the 90-degree turn, which is a worm gear. Now, for our conceptual design, after doing research and calculations, as you can see, we changed our last and final gear, which is the output gear, from a worm gear to a 90-degree bevel gear. This is because during our research, we discovered that bevel gears are more efficient than worm gears. Bevel gears have an average of 96% efficiency over a wider range of load ratios. So this is the input gear, which is a helical gear, the reduction gear, which is also a helical gear. Then the 90-degree is made by two bevel gears connected to the output shaft. Now, how we got our deflections and moment diagrams, we use a system called MD Solids. In this system, we took our shaft and we put it as a beam. We put the supports acting as, our bearings act as supports, and the load is the load from the gears. This is for the radial load, and this is the deflection that was calculated. This is the same radial load, same position, and this is the moment diagram using the same system. Now, for our torsional, what we did was we took the radial load and multiplied it by tangent of the pressure angle, which in this case we use 20 degrees as our pressure angle. Again, we have the shaft acting as a beam, the bearings acting as support, and the torsional load, and this is our deflection diagram. And same load and torsion with the supports, and this is our moment diagram. The structural design gears, For the first stage, like I said, the input gear is a helical gear, followed by the reduction gear, which is also another helical gear. Then we have our bevel gears, which creates the 90-degree turn in stage 2.
We use single row tapered roller bearings with a bore size of 3/4 inch, and it was made of bearing steel. A tapered roller bearing was used because it could handle the combination of radial load and thrust load. This is a cost estimate of our transmission system. We used 2 feet of 3/4 inch alloy steel for the shaft, and that came up to $15. All 4 gears came up to about $300. The tapered bearings, 6 of them, came up to about $130, and the casing, the cast iron casing, was approximately $90, which gave us a grand total of $537. For maintenance, we included pipe plugs on the housing to allow for easy fill and draining of the lubrication oil. The oil seal diameters had to be precise to extend the seal life, and lastly, standard screws were used for the casing to allow for easy replacement of the gears and the bearing. In conclusion, there are many applications for the right-angle transmission system, from the medical field to the heavy industrial field. There are also many different designs for this transmission system, using a worm gear, bevel gear, hypoid, etc. Standardized methods for the design and analysis of the gears, bearings, and shafts were used using AGMA or ASME. And further research would improve on the efficiency, applications, and would also reduce the cost of such a transmission system. Thank you very much.